I don't know if it's me, but okay, here we're on. So good time of day, everyone, and welcome to this new MLIR open meeting. And today we're gonna have an introduction to Linalg and Linalg.generic. You can.
Hi, everyone. My name is Yi. First, I will introduce my background. So I started working with Zhang Silvas on Torch MLIR project a few months ago. Our project, the goal of our project is to bridge the Torch world and the MLIR world so that we can run Torch modules end-to-end on the MLIR tech stack. And a big part of the project is that we need to lower the Torch operators from the Torch dialect to Linalg dialect. And we chose Linalg dialect because it's powerful and can model of most of the torch ops we need easily. And also Linalg dialect has very good backend support and good support in the MLIR ecosystem. So one of the backend we are using is ref backend, which essentially is just wrapping a few passes in the MLIR out of the box and then lower the Linalg dialect to LLVM dialect, and then can let the execution engine run the LLVM dialect. And then with this flow, our Torch module can be up and running without too much effort once we lowered into Linalg dialect. And another backend that can accept Linalg as input is IRI. It's another open source project based on MLIR stack, and it has its own set of dialect and a lot of optimizations with good performance and hardware platform support. So this is how we get the Torch module execute end-to-end pretty easily. Through this project, I got familiar with Linalg Ops. So today I will just share my what I learned, and from a user's perspective. There's a very complicated and rationale and design behind the Linalg Ops, but today we'll put those theory and philosophy behind us and just look at it from a user's perspective. Hopefully, by the end of the talk, a beginner to the Linalg dialect will be able to use it to implement some interesting tensor operations. So what are Linalg ops? Linalg dialects define payload carrying operations, which implemented structure ops. Structure ops just means the ops that carry out computation on tensors or buffers like contraction or convolution. And at a lower level, the structure ops need to be further transformed into loops or affine expressions with computation in the loop body. But at the Linalg level, the loops are abstracted away. So user don't need to worry about the details. And Linalg dialects already define some commonly used named ops that can let user use them out of the box, like Linalg.conf, Linalg.batch, matmon, and Linalg.pooling, etc. But under the hood, those ops are lowered to the Linalg.generic op. So Linalg.generic op is a building block for the Linalg dialect, and we'll take a closer look at the Linalg.generic op next. First, because the Linalg ops is used to describe tensor operations, I will use an example tensor operation here to illustrate. So suppose we have a tensor that has dimension NCHW, and we would like to perform sum reduction along the H and W dimension and get the sum result into a tensor with NC dimension. The corresponding Linalg.generic op in text form would look like this. There are mainly 4 components: the indexing map, iteration types, input operands, output operands, and compute payload. I will go into detail to explain in each of these components one by one. So the first one is the most straightforward one is iterator types. There's one iterator type for each nested loop, and it describes what kind of iteration the loop is. So currently, I think we only support reduction and parallel loop. So if there's loop carried dependency among the iterations, then the loop is a reduction loop. Otherwise, it's a parallel loop. And the C++ code to represent the iterator types are also is very simple, just a vector of string ref. And the next component is the indexing maps. So we have for each operand, no matter if it's input or output operand, there needs to be an indexing map. So each indexing map is a affine map. So on the left-hand side of the affine map are the induction variables. So for example, for a 4-nested loop, then there should be 4 induction variables. And on the right-hand side are the affine expressions of the induction variables. And those are the indexes used to access each scalar element of the tensor. So for the number of affine expression should be the same as the tensor dimensions. And next, we can look at some examples of the affine map. So for the first affine map on the top is for tensor A, and it's 4 nested loop, and the tensor also have 4 dimensions, and the indexes are just induction variables. And we have a special name for this kind of affine map. We call them identity affine map. And another example on the bottom is for tensor B. It's also for 4 nested loop, but tensor B only have 2 dimensions. So only 2 affine expression on the right-hand side. Given those indexing maps, what can we do about them? So let's look at some examples. Suppose the A tensor is an input tensor that has the affine map on the top, and the tensor B is the output tensor and has the affine map on the bottom. So if for an equation that let tensor B's element plus and equal to tensor A's element with this affine map, what this essentially does is to do a cumulative sum of the inner two dimension of tensor A and store the result into tensor B. So it's a cumulative sum. And in another example, if we let tensor A to be the output and tensor B to be the input, and let tensor A's each element equal to tensor B's each scalar element. What this essentially does is broadcasting the tensor B into the inner dimension of tensor A. So it's essentially a broadcast operation. And another example here is for transpose a tensor. So if the affine map on the top is for input and on the bottom is for output, both are two nested loops with a two-dimensional tensor. The only difference is that for the input tensor, the affine expression swapped the order of the induction variable. So, and for equation like B's element equal to A's element, what this essentially does is just transpose the input tensor and store the result into tensor B. So that is, hope those examples help you understand how the indexing map works and how it affects the access pattern for the tensor. And next, so we will look at the C++ programming to get the affine maps. So for the identity map, it's simple. There's existing API for constructing it, and for the other affine map, we need to first build the affine expressions. First build affine expression for D0, and then affine expression for D1. And then get the affine map. And so that's about the indexing map. And the next component in Linalg generic op are the input and output operands. So the input and output operands has one important purpose is that they define the iteration space. What this means is that the shape of the tensor decides the boundary of induction variables. So if a nested loop iterates along one dimension of tensor operand, then the induction variable shouldn't exceed the size of the dimension. And if the loop iterates along several dimensions of several operands, then the user needs to make sure the shape of those tensors agree with each other, so that the Linalg Op will guarantee there's no out-of-bound access inside the loops. And the output tensors have two uses. The first use is that it can be used as a shape-only tensor that is used to decide the result of the result shape of the Linalg operation. And when it's used for this purpose, you can see that there's no read access inside the loop body. And so it's pure, in this case, the initial value of the output tensor doesn't matter. It only serves as shape information. And also, in some cases, it's necessary because some induction variable bounds can only be decided by the output tensor. And another way the output operands are used is for destructive update. So in this case, the value of the output tensor is read in the computation and then overwrite with new values. Notice that in this snippet, the arc2 and Linalg yield are reading and writing to the same element of the output tensor. And essentially, what this code doing is let the output tensor element plus and equal to one element in the input tensor. So in this case, the output tensor need to be initialized with a valid initial value. And yes, and its initial value matters. And usually those are for reduction loops. And the next important component for the Linalg Op is the compute payload. It's actually the core computation of what the Linalg operation does. And it contains, it is a region, and the blocks in the region, the arguments of the blocks in the region corresponds to the scalar element of the input and output operands. So all the computation carried out inside the compute payload region are for a single element of the input and output tensor. And in the compute region, we need to use Linalg.yield op to write operation to write to output tensor. And in the arguments of the yield op corresponds to one scalar element of the output tensor. Also, the number of operands of the Linalg yield need to match the number of the output. So it's possible to have multiple output operands. And in this case, the yield also need to have the same number of operands. And this is how the compute payload look like in C++ programming. Is pretty straightforward. The value range args map to the scalar element of each operand. And another Linalg operation that's quite useful in and used often in the compute payload is Linalg index. This is used to get the index value along one dimension. For example, in this snippet, Linalg index 0 would equal to the value of D0, and in Linalg index 1 would equal to the value of D1. This is useful when you need to use the indexes to access some tensor that's not one of the Linalg operations and extract value from those tensors. And also, it's used for if, for example, if you want to get the indexes of the max value, it's handy to have this operation available. So that's pretty much everything about building Linalg Op. So and here's the code snippet. On the top is the text format for the Linalg Op to do the accumulated sum reduction, and the snippet on the bottom is the C++ code to finally build the Linalg.generic op and put everything together. So now you are familiar with each of the components, the indexing map, the iterator types, and input, output operands, and the compute payload. Yeah, so that's putting it together. That's everything about Linalg.generic op and how to use it from a user's perspective to implement some tensor operations. Hopefully, now you will also have chance to implement your own tensor operations and run some fun machine learning models. So that's it. I see a question. What if a single input tensor is used more than once and the affine map have two different in use case? How does ID index map to a tensor in that case? So I think you can have a single input tensor and use it differently in the loop. You just need to have different affine map. So the input tensor would appear to be two tensor operands. You need to list it twice in the input operands and have indexing map for each of these usage.
Oh, yeah, thank you. Yeah, I asked that question, and your answer is if I have that usage case, then list the same input twice in the input argument list.
Yeah.
And use a different map.
Yeah, that's my understanding.
And then for the index map mapping to inputs, then is it like 1-to-1? So for example, if you have 3 inputs and 2 outputs, then the index map needs 5 entries.
Yeah. Yeah.
And they will match in that order. So it's position based.
Yeah. Yeah, that's right.
Yeah, thank you.
Lorenzo has his hand raised. So Lorenzo, if you want to speak up, go ahead.
Yeah, thank you. So hi, thanks for the presentation. So I have actually a more general question. I need to generate the triangular loops. So have you ever had this such case when lowering PyTorch?
Triangular loops.
Right.
No, we don't really have this case. You you mean you need to like break early for certain loops?
I mean, I just need to generate a triangular loop. So let's say where, so I don't want a rectangular domain. I just want a sort of a triangular one. So I just want to know if I can adopt a sort of the iterator that Linalg generate to generate a triangular loop. So for now, I just use an if inside the body. The iteration space is still rectangular, but that's not what I want.
I see.
Sure, it makes sense.
Yeah, all my experience are based on rectangular shapes.
Right. Thank you.
Right, so I can comment on this if that's useful. So basically, the base precept is indeed to start with rectangular data types and iteration domains, and get those right to peak. But there's various ways to extend this. So for instance, today, Linalg works also with sparse data types, and then you get the sparse compiler. So one direction is indeed to use a control flow inside and then hope to hoist and canonicalize it away. But that is kind of a lot of work for not really a good high-level modelization. For the particular case of triangular loops, there's, I think, 2 directions that make sense. So we can have a different type of structured op, which would have simply iteration domains explicitly in the type. Like they don't have to be implicit like Linalg is today, like Linalg.generic is today. And then you would get closer to a ISL schedule tree, perfectly nested schedule tree type of thing. So that's certainly feasible. There's integer sets to do that in MLIR. The other direction is maybe go a little bit more in the direction that your colleague Daniele is going, is mostly using that in the data type, right? So you can have a triangular data type and have a codegen that's basically able to extract subsets of triangular things, mixing with rectangular domains. So I think these are 2 interesting directions, but they're definitely not available today. They're more like extensions.
Right. Okay. Okay. Thank you. Yeah.
Thank you, Nicholas.
Zhang, go ahead.
Yeah, I have a related question. This is about like the bounds of induction variable. I think earlier it was mentioned that the input tensor defines the bound. So it implies that the loop will go over like each and over element in the tensor. But if there's a case like, let's say I want to skip, if it's a 2D image and I want to skip the first and last pixel on both the left, right, and the top and bottom side, what would be the best way to do it today? Do I need like to create, is there a concept like a subview of a tensor and I have to pass it as an input, or in the index map, can I add like additional constraint?
Right, so that's exactly right. Today, with the Linalg generic today, you would use the subview, memref subview, so it's a subview of a buffer. And the equivalent in the tensor is a insert extract slice. So you would constrain your data type and then keep a rectangular operation on that new data type. If or when we have more powerful structured op, you could encode it directly in some iteration domain, directly in the op. But today you would use indeed more a data type driven model than a iteration domain driven model. Does that make sense?
Yeah, it makes sense. Thank you.
I guess since there's a lull, I'll take this opportunity to ask the question that I guess was off topic that I pasted in the chat. So Yi, thank you, by the way, for the presentation, posted this slide, had the slide about transposition, right, where you could use affine maps to perform transposition pretty easily. And like I mentioned in the comment, this came up in some debate on Hacker News. So the affine maps are something about polyhedral compilation, right? You want affine representations of the iteration domains, something like this. And so it occurred to me, like, I wonder if you could find transposition. Somebody said you could speed up matrix multiplication by, taking the transpose of one of the matrices and for cache locality. And I thought you could not encode transposition as one of these transformations, but that clearly, like, that should have come to mind immediately, was wrong. Could a polyhedral compiler find this in order to optimize for cache locality? This is not about Linalg, but just curious if anybody.
Oh yeah, absolutely. I mean, it's been done a bunch in the literature, right? So I guess maybe the main question is, so I guess one thing to consider is that there's different areas of polyhedral compilation. So maybe the most classic one is affine scheduling, which basically reorders your index space iteration in the transform program. So that one does not touch the data itself, but by just traversing the data or the computation in a different order, you kind of get this transposition effect as a function of the accesses. So if you permute two loops, for instance, you can get this better locality, except when you permute two loops, you're going to change the order of traversal of all the loads and stores beneath it, right? So A, B, and C. So if there is a good loop order such that everything is contiguous, yes, polyhedral technologies will find it, or at least affine scheduling will find it. Then you have data layout transformations, which operate just on the, I guess, the buffers themselves, but do not touch the iteration domain. And that would be more of a restructure the affine map that accesses the data, and that would be on each load and store. And then you have combined things. And so to kind of tie Linalg into this, Linalg is a combined version of these things with some additional restriction. But certainly you can also do some of these things in the polyhedral world. In fact, you can do more in the polyhedral world, but it's also much more difficult to manipulate, basically.
Yeah, that makes sense. And just follow up. The question of whether a compiler would be able to find this is basically like whether you encode the cache locality in the, what is it called? I think it's called a cost function or something like that.
Yeah, like we literally implemented this thing. So I think, let's see. I mean, there's a breadth of literature, right? So I think the first one who implemented, a good polyhedral scheduler that really solved some problems was Ude in 2008. Then we did a bunch of work at Reservoir Labs on a bunch of constraints that are related to contiguity, symmetrization, locality, etc., etc. There were a bunch of papers also on something called consecutivity by Alex Zinenko, who's also working on MLIR a lot. So yeah, I mean, the literature is vast, and depending on which particular part you want to focus on, like, there has been formulations. Yeah, I'm happy to follow offline with references.
Cool.
If you want.
Thank you. Thank you.
Any other question on Linalg in general, or anything related to this? Feel free to ask anything. We have time, and we have Nicolas here to answer questions about anything, or many other people can answer questions. So if you want to know anything about Linalg or future plans, or anything that is not clear, it's the time. Yeah, go ahead, Suraj.
Hello. So I have a question about Linalg. Has it been used in a use case where the final computation is not a two-dimensional multiply and accumulate, but some kind of three-dimensional primitive? For example, multiply, accumulate, perhaps in a particular dimension, like a channel-wise dimension. Say if you want to be able to handle multiple channels or multiple elements along a particular dimension, and express that using some kind of a low-level primitive in hardware. Is there such a use case, or has it ever been used in that kind of way?
So I'm not completely sure I get the connection to the lower level primitive, but let's just say that we can do convolutions and all these things, and transform them and map them to lower level things. So at that level, we could, if some hardware had a, I don't know, dilated convolution unit, we could generate that after transforming and tiling and doing stuff on it.
Yeah, so an example here would be, say you have some kind of a hardware primitive or a low-level primitive that can accumulate the multiply addition along, say, input channels worth of results. So you go through the HW plane for maybe 10 input channels, and then you do the multiply accumulate of the input feature map on the right, and sort of add along those 10 channels, and that can be a single primitive, and you want to export that somehow within Linalg. I wonder if that's something it can expose.
Yeah, absolutely. I mean, the way we would consider it is basically take any higher level primitive that you're interested in, let's say some convolution, then you do some specific tiling that at the lowest level needs to match your hardware primitive.
Yeah. That's what I was thinking of.
Yeah, and then you basically, what usually ends up happening is you have some dimensions that are tiled by 1. These are basically folded away, and you reduce, I don't know, let's say a 7D convolution to a 3 or 4D primitive. And that's the thing that you can map. Like, let's say if your primitive is, I don't know, 4 by 7 by 32, just why not? Yeah, that's very easy to do. It's literally like two or three transformations composed together, and even in Python today, and you just get that out of the box.
Right. Thank you.
Yeah, sorry, I have a follow-up question. Actually, I was trying to digest what Nicolas just told me. So I have a question. I mean, the second point was essentially to have this structure, encode this structure into the type. But I mean, I think, and with Daniele, we actually were considering these things. But the point is that we are going to end up what ISL was doing, right? Where you have your iteration domain, your access relation, and then you try to intersect and generate a loop. And I mean, would be this the right direction to go? Because I mean, I feel that it's really a lot of work. And I'm not sure if you could do that today with the infrastructure that MLIR has.
Oh, it's definitely a lot of work, and triangular is, let's say, the baby step forward. But the plan is to go significantly further. So, I mean, sparse today has its own compiler that already does stuff in a much more general way than just triangular, right? It's like much more powerful already.
Right.
And basically, what is, I guess, the missing link today is that in the sparse world, I would say the kind of the tile size that you target is always 1, 1, 1 everywhere, because that's what's easy to start with. So basically, we kind of want to lift this notion of subsets that are relatively easy in a dense case, right? It's just a subview or a subtensor. Try to lift that to richer data types. So in the sparse case, for instance, that would require inspector-executor kind of stuff. And yes, it's going to be a lot of work. Triangular is a baby step from what we have today towards that, but we're aiming for the bigger thing, right? And so there's a lot of cross-pollination that is waiting to happen with, let's say, the database community. There's something called the collections virtual machine that's really interesting. Yeah, lots of stuff along that direction.
Okay.
But I agree that for the very simple thing you want to do, which is, well, I just want some triangular stuff, it is probably much more work than you would like to just get the triangular stuff. However, the much more work will solve the general problem, which is really the reason why Linalg exists. Otherwise, everyone could just do a fine.
Right. But I mean, one question that I don't, I mean, one thing that I don't understand, I mean, the sparse tensor compiler, do they already go in this direction? Because I mean, as far as I understood, they were just working the Linalg generic and building a sort of a set data structure that they were then optimizing and using to meet the AR. Or is my understanding not correct? So
I mean, Art is definitely the best one to comment here, but I guess my interpretation of the thing is basically that if you go directly from a Linalg plus data type representation to loops that iterate one iterator at a time in some loop order, and then the loops may be data dependent on other stuff that happens in previous loops, it's basically tiling by one everywhere. That's really the motivation here. In the same way that you say, hey, I'm doing loop fusion, then I would say, well, yeah, sure, loop fusion is fusion on Linalg if you tile by one. Basically, it's the same type of thinking. The challenge is, how do you not tile by one? Because when you tile by one, well, it works. I mean, that's definitely the first thing to do, and it allows you to capture I would say the order of magnitude improvement. Let's say in sparse, for instance, what's really important is being sparse, not so much iterating on multiple, co-iterating on multiple iterations at a time. But the general setting of taking a subset of the data and a subset of your iteration space is something very general. And loop-based transformation are just saying my subset is of size 1 everywhere. And what we're trying to do is to lift that to multi-dimensional subsets of sizes, whatever, along each dimension.
Okay, thank you.
Any more question or topic to discuss? Feel free to ask them by writing as well in the chats if you prefer not to speak up.
I guess I'll ask another question since nobody has asked.
Yeah, go ahead.
So Nicholas, I actually made contact with you a couple of weeks ago about comprehensive bufferization. I was doing something, it's now been a couple of weeks and I changed tracks a little bit, but there was some left there to figure out whether comprehensive bufferization would work. I'm not sure if you remember this. Maybe we should just continue to discuss it offline.
I mean, I don't remember the detail. I mean, I remember that you posted a bigger example, and then Matthias picked it up, and I think his comment at the time was that should work now, but I don't think it was conclusively closed. Maybe do you have a way to repro? Because
I mean, that flow is completely reproducible. Like I get that out of a pipeline that I can run at any point. So yeah, okay. So I'll talk. I get another thing that we should talk offline about, I guess.
Right. Yeah, I mean, feel free to ping Matthias on the same thread. My recollection is that he looked at it and said, "Oh yeah, that should be fixed now." And yeah, but we didn't have a way to repro it. I think.
Sure.
I don't remember. Yeah.
Okay, cool. Thank you.
Sure. Nothing further? I'm going to make a last call for more questions. And otherwise, we may just leave it there. Okay. Well, I think this is the end. We're going to claim back the last 10 minutes of the slot. Thank you again, Yi, for this presentation. I think that will be very helpful for anyone getting started with Linalg. We probably should have more beginner sessions on some areas of the compilers and some dialects in the future, hopefully. And that's it for today. Thanks everyone for joining, and see you next time.
Thanks everyone for listening.
Thank you.